Hey everybody, and welcome to this new lesson, which is searching. We will make an introduction to searching, then we will discuss about linear search, and then a much better search, which is the binary search. So let's start. So, as the name suggests, searching is the process of searching for an object in a set of objects. For example, searching for a number in an array, or searching for a string in a dictionary, or a set of strings. Or we can search for an object or maybe more objects which have a specific property in a set of objects. For example, searching for a peak element in an array. Or we can search for a subarray or a subsequence. For example, searching for a subarray of given sum, searching for the maximum sum subarray, or searching for the longest increasing subsequence. All of these are classical problems which we will solve in the next chapters or in the learning path. Now let's stick with the simplest and most important problem of searching. We are given as input an array A of n elements and an integer target, and we should return the index of the element equal to target, or -1 if there is no element equal to target. This can be done with a linear search, which is indeed a brute force approach. And what it does is iterating through each element of the array until it finds one equal to target. If it doesn't, at the end, we return -1. As you can see, we are performing a constant number of operations, which are return I, the if statement, and maximum one time returning -1. And because the for loop makes maximum n iterations, the time complexity of this approach is big O of n. We had to iterate through each element of this array because the array A contains unordered values. And because we really don't know where the target value could be, we have to try out each and every one of them. But what if we are searching for a number in an ordered array? Let's have as the input the non-decreasing array A of n elements and the target value. As the output, the same, the index of the element equal to target, or -1 if there is none. Of course, we can still do the linear search, and we can add one little optimization. And that is, if the current value is strictly greater than target, we can return -1, as we know that all the values after this one are going to be greater than target. But this for loop still makes n iterations in the worst case scenario. Take for example, searching for a value which is greater than every value from the array. We still make those n iterations. So the time complexity is still big O of n. But we still haven't used one property to its full potential, and that is that the array is non-decreasing. And here binary search takes place. Let's find more about it. Let's say nums is our array, and it has n elements, and it is non-decreasing. We will denote the searching range by two pointers, which are left and right, initially on 0 and n-1 respectively. While left is less than or equal to right and we still haven't found our target value, we will compute the middle position, which is floor of left plus right divided by 2, and we compare the element on that middle position with the target value. And there are three possible scenarios. Either nums of mid is less than target, so all the elements on its left are also less than target, which means that there is no point on looking for the target value on the left of position mid. So we can reduce the searching area to the range mid +1 and right. And of course, we do that by setting left's value to mid +1. The second scenario, in which nums of mid equals target, which is straightforward because we have found our value, so we should return mid. And the third scenario, where nums of mid is greater than target, and because the array is non-decreasing, all the values on mid's right are also greater than target, so there is no point on looking for target there. This means we can restrict the searching area to the range left mid -1, and we do that by setting right's value to mid -1. Now let's take a real example to have a better look at how this works. Let's say this is the nums array and the target value is 8. We start with left equals 0 and right equals 8. Left is less than right, and we haven't found the target value, so we will compute the middle position, which is floor of 0 plus 8 divided by 2, which is 4. Nums of mid equals 10, which is greater than target. And indeed, every value on its right is also greater than target, so we will set right to mid minus 1. Mid is floor of 0 plus 3 divided by 2, which is 1. Nums of mid equals 2, which is less than target, so we will set left to mid plus 1. Mid is now floor of 2 plus 3 divided by 2, which is 2. Nums of mid is less than target, so we will set left to mid plus 1. Now left equals right equals 3, and mid of course equals also 3. Nums of mid is now equal to target, so we have found our solution and we will return mid. Now let's compute the time complexity of this algorithm. As you can see, inside the while loop, we perform a constant number of operations. So the real question is how many iterations does this while loop makes at most? Let's see what happens. On iteration number 0, so at first, we are working with a searching area of length n. On iteration number 1, there are 3 possibilities depending on what scenario we are on. If nums of mid is less than target, then we will be left with a searching area of length n divided by 2. If nums of mid is equal to target, then we are done. And if nums of mid is greater than target, we will remain with a searching area of length n divided by 2. Then, after the second iteration, the tree of possibilities gets wider. From the first previous scenario, there are also 3 possible scenarios in which we will remain with a searching area of length n divided by 4, or we are done in the best case. Same, from the third possible scenario, we have also 3 possible scenarios, and we will remain with a searching area of length n divided by 4, or best case scenario, we are done. Let's not forget, on each of these iterations, we are performing a constant number of operations, and so on and so forth until we find a solution. How many iterations does this algorithm do in the worst case scenario? The worst case scenario is that in which we never find the target value, and as you can see, we always remain with a searching area of length half than the previous one. So from n to n divided by 2, n divided by 4, n divided by 8, and so on and so forth until length 1. This is a total of log of n iterations, and the time complexity is big O of log of n. Some real-life applications of binary search are the problems in which we will search values in sorted arrays, or we will search for a value in a monotonic function, or we even search the answer of some problems, and we will see more of that in the learning path.